Everybody can see the PowerPoint?
Yes.
Okay. All right, so tonight we're going to go into chapter 7, which is a bunch of different ways of integration. So you've learned one already. That was the substitution method where we plug in the U for something and we actually do it that way. That's one method of integration, which works pretty well. That's actually the opposite of the chain rule that you do in differentiation. So every rule in differentiation has a subsequent rule in integration that allows us to work with it. So the one we're going to look at tonight is integration by parts. Integration by parts is the corresponding rule is the product rule for differentiation. So the product rule for differentiation states when we're multiplying f of x and g of x, go back, we have f of x times the derivative of g of x plus g of x times the derivative of f of x. So everybody remember that rule from Calc 1? Okay. So if we take that function right there and we start solving it, so if we do the integral of both sides, the derivative and the integral cancels each other out. So that would just be the f of x times g of x. And then we do the integral of the other side, so the integral of f of x g prime of x plus g of x f prime of x. We can break that up. And we're going to start rearranging the problem so we can do some work with it. So if I take the f of x g prime of x and then move the other one over so that I can say that equals f of x times g of x minus the integral of g of x times the derivative of f of x. That function, that equation right there is the formula for integration by parts. We're going to look at it in a lot simpler context in a second, but that's in essence what we did. We took the product rule and we did the integration of it to actually get the rule to undo the product rule. The way we're going to look at it is we're going to look at it with the u and the dv because it makes it a lot simpler to look at. So u is f of x and v is g of x. So that's u, so that's f of x. dv would be the derivative of g of x. So that's uv. And then I have g of x times the derivative of f of x. All right. Not sure why the whole integral symbol isn't there, but it should be a regular integral symbol. So I would write that down because that's going to be the key to doing pretty much every other problem that we're going to be doing tonight. All right, so let's look at this example. This is the only example we're going to do that they're going to have written down. And then we're going to do probably about 6 or 7 examples. Actually, I think we have 8 examples that we're going to do that I'm going to do out by hand and show you step by step how we do everything using the U's and the V's and stuff. So in this one, it's separated quite nicely. We have the X, when we have sine of X, and then we have the dx. The key when we're looking at these things is how do we split the problem apart to figure out what we're going to make the f of x and what we're going to make the derivative of g of x. And the key piece of that is because when we do the derivative of g of x, to find g of x, I have to do the integral of it. If we have f of x, to find the derivative, to get d of x, or the derivative of it, I just do the derivative of it. So we want to pick things that make our lives easier and simplify the problem down. So if I take the derivative of x, I would get 1. That definitely simplifies my problem down. Where if I took the derivative of sine of x, I would get cosine of x, which doesn't really help me much. It doesn't really change the problem. So I'm going to set my f of x to x, and I'm going to give you a list of how we pick this, and after we're done with this example. And we're setting my derivative of g of x to sine of x. So we do the derivative of f of x, and we get 1. The integral of sine of x, which gives me negative cosine of x. Now we're going to plug those back into my function. So the beginning is f of x and g of x. So I have x and negative cosine of x. And then it's minus the integral of g of x, which was negative cosine of x. And the derivative of f of x, which was just 1 dx. Now my integral is, I'm just doing the integral of cosine of x. And the integral of cosine of x is sine of x. So I can do that integration. So my answer is negative cosine of x plus sine of x plus c. Once we start doing them out and I'm using the v's, you'll understand why those are a little simpler, and the setup I'm going to make will make your lives a lot simpler when you're working through these problems. But I wanted to show you at least one example using the f of x and the g of x. Same problem. All right. So there's a mnemonic device, just like PEMDAS and those, that helps us figure out which value of u we're going to choose. So which is the one that we're going to take and do the derivative of it. In order that is, it's logarithmic problems are first. So your ln's, your logs, those type of things. Any inverse trigonometric ones are next. So that means your arc, cosine, arc, sine, arc, tangent. Then any algebraic problems. So that's your x's, x squares, those type of things. Then trigonometric. And the last thing you want to use is exponential. So that's how you're going to choose your u. Whatever part is the u, the other part's got to be your dv. Okay. All right. Give me a minute to finish writing that down, because that's going to be your key piece. That is not in the book. I don't know why it's not in the book, but that is not in the actual textbook. So making sure you have that written down is going to make your life a lot simpler when you're going through doing these problems out. Because that's always the hardest thing, is which one do you pick to do first. And if you pick the wrong one, the problem gets more complicated. And you can get stuck in loops, which makes you have to do a lot more work to solve it out. All right. Yep, good. So now I'm going to share my other screen. All right, so you should be seeing my Jamboard, right?
Not yet.
Okay. Let me try that again.
No, it's still the black screen.
Okay. There we go. That's what I wanted. Now everybody can see it, correct?
Yes.
Okay. Is it really blurry, or can actually see the problem pretty well?
It looks fine.
Okay. Awesome. All right. So when we're setting up these problems, I always set it up as u du and v dv. So we're going to plug in the two pieces that we're going to get from the problem is u in DV, and we have to find the other pieces. Okay. So in this problem, the only thing I actually have in the problem is the ln of x. So I don't actually I'm back now. Apparently they're working on the internet on my street. I don't know why. Can everybody hear me or no?
Yes.
Yes.
Okay.
You're back.
So in this problem, I only have ln of x. I don't have another piece. So if we look at that rule that we had written down from the last slide, the first thing in that list is logarithmic. And the reason why we want to make our logarithmic the u is because I can do the derivative of a logarithmic, but I can't do the integral of it. So I'm going to make my u ln of x. And I'm going to make my dv just the dx. So what's the derivative of ln of x?
One over x.
Correct. So it's 1 over x dx. Yeah, just put the 1 over x. You don't really need the dx there. And then the integral of dx is x. So now we can go back and we can plug in based on the rule. So remember, the rule was the integral of u, oh, sorry, is u v. Sorry, my u's are looking like these, minus the integral of v du. All right, so now we're going to plug the values in. So u is ln of x, v is x, minus the integral.
Where did that second x come from?
Which one?
V, because isn't u the whole thing already? ln x?
No, yeah, so u is ln of x, so dv was dx. Hold on, let me finish writing this and all. Okay. Third time's the charm. Can everybody hear me now?
Yep.
Yes.
Yep.
Okay. Let's try this again. All right. So can you see down the bottom where I wrote the integral of the ln of x dx? I'm not sure which you heard and which you didn't hear, so I'll repeat this little piece. So the ln of x is my u, and the dx is my dv. You have to remember that you can always have a 1. So it's really 1 dx. You just don't have to write the 1. So that's how we're allowed to make the dx that actually be part of my integration by parts. So, and that's where that other x comes in, because the dx, when I take the integral of dx, it's the integral of 1 dx is x, because that 1 becomes dx. Does that make sense?
Yep.
Okay. So then I've got my problem over here. I've got the ln of x times x. So I'm going to rewrite that as x ln of x minus, then I have x over the, and times 1 over x, which is just 1. So that's 1 dx. So this is x ln of x minus the integral of 1 dx is just x. And then we add the plus c on the end. So that is the integral of ln of x. Is x ln of x minus x plus c. Give you a minute to finish writing that one down. And is there any questions or anything else on that one? Everyone we're going to look at slightly different in how it's set up and done. So this way you can see a bunch of different ways to do these problems. All right. Next one. So the next one we're going to look at is t squared e to the t. So first thing we're going to do is we're going to set up our u du and v dv. All right, so using the mnemonic, which one are we? So we have right now, I have t squared e to the t dt. So I've got t squared and e to the t. Which one of those two am I going to make the u?
E to the T.
All right. So let's make that e to the t. And that means my dv will be t squared dt. Okay. So what's the derivative of e to the t? What's the derivative of e to the t?
Would it just be e to the t again?
It would be.
I see.
All right, so that's e to the t. What's the integral of t squared?
T cubed over 3.
Very good. All right, so let's write the problem down now. So u is take 4. All right. Let's reshare this. Okay. Can everybody see the problem again?
Yes.
All right. Okay. So I don't know where I dropped off again, but so I finished writing out the problem. And actually, this isn't a horrible thing I dropped off again because I wanted to actually notice something in this one because we're going to have to redo it. What do you notice happened to the integral in the new problem? Did it make it any easier?
No.
No. We still have t to the we now have t to the third over 3 when we started off at t squared, and we still have the e to the t. So the problem didn't get any simpler for me to work with. So if we go back to that mnemonic that we were looking at, you'll notice that the very last one in the list is exponential. And the reason for that is when you take the derivative or integral of an exponential, it basically stays the same, especially e. So doing that is never going to actually change anything. So you always want to make that your dv. Because since it's not going to change anything, that's fine because we're not using that in my new integral anyway. So when we're looking at this, you really want to make the other one. So what we wanted to do is my dv is e to the t, and this will be t squared. So my derivative of t squared is 2t. The integral of dv, dt. The integral of e to the t is just e to the t. It stays the exact same. So now when we plug it into my problem, I have t squared e to the t minus the integral of e to the t 2t dt. Now, the problem didn't get necessarily simpler, but we're moving in the right direction. because now I've taken my t squared and now it's become 2t. So it's definitely getting smaller. However, we still have something that I have to do integration by parts again. So I now have to take this part of the equation and do my integration by parts again for that part. So I have t squared e to the t minus 2. And then we're going to do integration by parts on that piece over there. So we're going to erase this part down here. And we're going to do a similar thing again. What we're going to do is this time we're going to do the u du and the v dv again. And I'm going to use the same thing. I'm going to make my u t and my dv e to the t. So now the derivative of t is just dt. The derivative of v, or the integral of v, is e to the t. So now when I redo that part, I have t e to the t minus the integral of e to the t dt. Does that part make sense? So this one, we actually have to do the integration by parts on it twice to get it down. And that's why even algebraic is not at the top of the list, because algebraic only goes down one step at a time when we're doing exponents. So it can only go from, if it was t to the 5th, we would have to do this integration by parts 5 times to get it down to nothing. And the funny part about it is when I made my tests in the past, I would take problems from the book that we've done in class, and I'd make them the test questions by just changing a number. And I did that on this question. I actually changed it from t to the 2nd to t to the 5th. And not even thinking, I'm like, oh, it's just changing one number. And then when I was going through and doing the answer sheet, realizing I had to do it out 5 times while the kids were taking the test in the class, they were not happy with me that test. So that's why algebraics after logarithmics and stuff, because those drop down really quickly, and we can do the integration of a t squared to get rid of it. So that's not that hard of an integration to do. But the e to the t never changes. So that's why making it the u wouldn't help us very much. All right, so let's go through and clean this up and get to my final answer. So the t squared e to the t is there. Then I have minus 2 t e to the t. And then e to the t, the integral of e to the t is just e to the t. So I have plus 2 e to the t, and then plus c. And that's my final answer. Questions on that one? You can see how writing things down and actually doing it out and writing all the steps is going to be helpful, because if you don't, you can get lost really quickly in these problems. And colors are always nice to keep track of the things, or you can use different letters. Like you don't have to necessarily use UDU again in the next one. You can use any letters you want. You just have to remember which ones go where. So a lot of times they'll use the U on the first one, and then maybe they'll use like M and N on the next one. You just want to try to use a letter that they don't typically use in the actual problems. All right, let's look at the next one. All right, so this one, we have the integral of e to the x sine x dx. So my two pieces that I have e to the x and I have sine x. All right, so what do you think we're going to use for this one? What's going to be the u?
Would it be sine x?
Yes, because remember, basically, the only time you never really want to make it exponential. Anything other than the exponential, unless you have two exponential ones, and then we can do something else with it. So in this case, it's going to be sine x is my u, and my dv will be e to the x dx. So then the derivative of sine of x is cosine of x. And the integral of e to the x is just e to the x. So, flick this back into my problem, and we get e to the x sine x minus the integral of, we have e to the x cosine x dx. Now, my integral didn't get necessarily any simpler, but it did change a little bit. So let's do this one. So now, let's do color. My u is going to be, right, my u du and v dv. So u, since we used u as sine of x this last time, let's do it as cosine of x this time. Again, because I still have my e to the x, so that's going to be my dv. So that's still e to the x. The derivative of cosine of x is what?
Sine of x.
Almost.
Negative sine.
Yeah, don't lose your sign. So it's negative sine of x. All right, so we have e to the x sine x minus, and then I have e to the x cosine x minus the integral of e to the x minus sine of x dx. All right, so let's clean this up a little bit. So I have e to the x sine x minus e to the x cosine x. And then I have minus the integral of e to the x sine x. All right, so what do you notice about my new integral?
That's what we originally started as.
Exactly. And you're like, great, we're going around in circles. Well, yes, we are. However, we do have some other stuff left in my problem here. So whenever we're solving a problem out, this is one of those things that we rarely do, but is always there. So technically, when you're solving a problem out, you should be writing the other side of the equation for every step. So we have this. Let's see if I can write this small with my hand so I can finish writing it in one line. So you have two sides of your equation, and we can manipulate those two sides of the equation, the integral, to both sides because they're the same. And I have 2 integral e to the x sine x dx equals e to the x sine x minus e to the x cosine x. And if I just divide both sides by 2, we get my answer as e to the x sine x minus e to the x cosine x over 2. And that's my answer. So, plus C. I forgot the plus C at the end. So if you find yourself seem to go around in a circle and you get right back to where you were at the beginning, remember this. that you have that other side of the equation. So if you can bring it over to the other side again, you have what's left over, and you can just divide by the 2 at that point.
I have a quick question.
Yep.
That writing in red, you see how it's the negative sine x there?
Yep.
Why in the next step is it just the sine x?
Because I, in essence, had 3 negative signs going to that one problem. And I'm glad you asked, because I figured at some point somebody was going to catch this and go, didn't lose it. So for that, this negative sign right there, which is in front, is made up of that one, and that one. Because technically these 2 signs right there, because I can pull out a constant, makes that a positive, and then I'm multiplying it by a negative.
Okay, that makes sense.
Good question, though. All right. Any other questions with this one? Okay. Next one, let's do some inverse trig functions. All right, so now this one is also a definite integral. So we're going from 0 to 1 of tangent negative 1x dx. So for this one, I have my tangent negative 1, and I have my dx. Those are going to be the 2 pieces I have for this problem. So I have my u du and v dv. So which one am I making my u?
Tangent to the negative 1.
Yes. Because that's an inverse trig function, and it's before algebraic, which would be my d to the x. And that's different, because if it was just sine of x, I would have reversed what you just said. The x would have gone first, because algebraic's before the trig. So those are the little things to keep in mind at that point. So in this case, that's going to be the tangent negative 1 of x, and that would be d dx. So this one's simple. This one's x there. Now, what's the derivative of the inverse of tangent? You might have to look it up. This isn't one that most people have memorized, including myself. This is one of those things. Remember I said you guys get an index card for the tests? This is the type of things where, like, if you have to look it up when you're going through and doing your problems, especially for the review for the test, put it on an index card, so this way you have it right in front of you at that point. So, and I try to make, like, because I'm doing it on WebEx this time, so I'm hoping that they're going to be similar type problems. Like if it's an inverse trig function, it's going to be an inverse trig function for all the different types of problems there. So, because normally I try to make my sample test similar, just with changing of numbers. So this one ends up being d of x over 1 plus x squared, because the derivative of tangent, inverse tangent, is 1 over 1 plus x squared. All right, so let's go through and write out my problem. So I have x inverse tangent of x minus derivative of x over 1 plus x squared dx. All right. So how are we going to do that integral? The x over the 1 over 1 plus x squared.
Would we do substitution?
Yep, we can do substitution. What do you want to make your u?
Would it be the 1 plus x?
Yeah, it'd be the 1 plus x squared. So therefore, du is going to be 2x dx. And since I only have 1x, I'm going to bring the 1/2 over. So 1/2 du equals the x dx. So that integral part, the 1/2 can go out front, and I'm left with 1 over u du. So what's the integral of 1 over u?
Would it be the ln of u?
So that would be the ln of u. Good. All right, so now if we're going to go back to my original problem that I had, so I have x, the inverse tangent x, minus, and then the integral is 1/2 ln, and my u was 1 plus x squared. And we're evaluating it from 0 to 1. All right. So if I'm plugging in 1 to this whole problem, I have 1, the tangent -1, or the arctangent of 1 is, was it pi over 4? So I have 1 pi over 4 minus 1/2 ln, if I plug 1 into there, of 2. And if I plug in 0, I get 0 times 0 minus 1/2 ln of 1. So the 1/2 ln of 1, ln of 1 actually is 0. So this problem comes out to be pi over 4 minus 1/2 ln of 2 is my final answer. And when you're doing a definite integral, you don't have to put the plus c at the end because you've actually done it out and got the exact answer. All right, we got a few more problems we're going to do. I think I got 4 more problems we're actually going to do before we're done for the night. But the next problem, I'm going to actually give you guys about 5 minutes or so. My hand needs a little bit of a break writing. I'm going to have you guys work it out, do it out, and then I'm going to do it out after you guys are done. So I'll give you guys about 5 minutes to go through and do it. So there you go. It's the integral of x cosine of 5x dx. So take a few minutes to work through that, and I will be right back. All right, since everybody's probably at least past this part, if you haven't yet finished, that's okay. But look at my V, my dV, and my V. So you should have had du as x or and then the du as dx. dV was my cosine 5x. V is a 1/5 sine 5x. If you do not have the 1/5 there, you need to make sure you have the 1/5 there. The reason it's there is because you're doing basically what's known as implied substitution. We have a 5x inside. So when I take the integral of cosine of x, it's sine of x. But I'm not doing the integral of cosine of x. I'm doing the integral of cosine of 5x. So you have to do u substitution. You're making that 5x your u, which would be your sine of u. The derivative of 5x is the 5 dx, and that's where the 1/5 du comes into play. So that's where that 1/5 comes in. You don't necessarily have to write the steps out. That's why we call it as implied substitution. It's something that you want to keep in mind though when you're doing these problems. Don't lose that term inside. It's not just, oh, the integral is going to be the same. That term means something. So that's where that 1/5 comes into play. So, and there's actually another place a little bit later in the problem where you have to do the 1/5 piece again because you have to do the integral of cosine of 5x. So that would be your final answer in this problem.
So you wouldn't like you wouldn't find a new u and du and v and dv for the sine of 5x.
No, because we don't have. So I can do the integral of sine of x fine, or whatever it is. So since I can just do the integral and there's no other parts, I don't need to do integration by parts again.
Okay.
I would just do the simple u substitution at that point for the 5x.
Oh, I see what. Okay. All right.
And that's where the 1/25 comes from because it's the 1/5 originally, and then the 1/5 again from doing that and implied u substitution again. All right. Next one. All right. Take a couple minutes, work through this one. So this one, your U should have been the ln. Your dv should have been the t to the fourth. So du is 1 over t and v is 1/5 t to the fifth. So we get 1/5 t to the fifth ln of t minus, and then I always try to pull out my constants there. It makes your life a little bit easier in doing it. So I get the 1/5 and then the integral of t to the fifth over t, which is just t to the fourth dt. So I get 1/5 t to the fifth ln of t. And then I have 1/5 times 1/5, which gives me my 1/25th t to the fifth plus c. Do make sure you're being very careful with your signs and your fractions. I don't know how picky ExamView or WebAssign is. And actually, like, if you put the wrong exponent, it's probably going to mark it wrong. If you have the wrong number, it's probably going to mark it wrong. And I'm not exactly sure how much information it gives me on the other side when you do it. So I will have a practice one put up tomorrow. That's what I'm going to work on. I'm going to have the practice assignment, and then I'm also going to have the practice test for chapter 5 and 7 up tomorrow. So you guys can start working on those, and I can get some information on how it actually does it for the real test, which will be in 2 weeks. So, all right. 2 more problems. All right, let's try this one. This one's a definite integral. So once you get the integration, you're plugging in 1 and 5 to it. This is the time that I miss the classes because I used to be able to walk around and see what you're doing, fix little mistakes people are making. And now I can't see what anybody's doing. But please, if you are getting stuck and what you're doing isn't the same as what I'm getting there, and you can't figure out based on what I'm explaining it, say something. Don't get totally stuck. Out of all the techniques of integration we're going to do, this is the simplest one. So they get harder from here. So, and a lot of them starts building on each other. So you might have to use this and the partial fractions or a trig substitution or something like that in it.
Professor,
Yes.
the 1 over r, would that be 1 over r squared? Like the two of them just multiply and then is it becomes 1 over r squared? Is that right?
So this right, so hold on, okay. So that right there, that's 1 over r squared.
Okay. Okay.
So when you do the integral of that, you end up getting negative 1 over r again.
Oh, okay.
So the reason I threw this one in there was we were dealing with fractions, and a lot of the integration that we've been doing is just with like x squareds and those type of things. And sometimes when you have basically negative exponents, people will make little mistakes on those. So that's why I wanted to throw that one of those in there.
I'm not understanding why when you integrate it, it becomes negative 1 over r.
Because it's r to the negative second power. So when we integrate the r to the negative second power, it becomes r to the negative first power divided by negative 1.
Okay, thank you.
No problem. That's actually the exact reason I put a problem meter like that, is so you can see those little things, because we don't do those type of problems very often. So then the final answer ends up being negative 1/5 ln to the 5th minus, or plus 4/5, because I have the negative 1/5 plus 1, which gives me the plus 4/5. All right, one more problem. So we're doing the integral of e to the square root of x. So yes, this problem is in integration by parts, so we're probably going to have to do that. However, looking at this problem, what would be the first thing you would think to try to do? So if it was just e to the x, the integral of e to the x is what?
E to the x.
Right. The problem with this one is I have e to the square root of x. So I have to do something with that square root of x to be able to do this integration. So the only, like if it was e to the 5x, I would just do a u substitution with the 5x. That's what we have to do with this one. So we're going to do a simple u substitution on this one first. So I'm going to actually use m. So I'm going to say m is the square root of x. So that means a dm. So the derivative of the square root of x, so remember that's x to the 1/2, is, oh, actually, you know what? They do it a different way. Hold on. Which makes our lives a lot easier. So m squared is x. So if we do the derivative of both sides, we have 2m dm is dx. So this problem now becomes the integral of e to the m 2m dm. that make sense?
I think so.
So the goal is to get rid of that square root so I can have just e to the something that then I can do the integral of that one. So if we did the derivative of this, you'd end up getting 1/2 x because you bring it down to the negative 1/2 or 1/2. So then you have a division in there, which makes my life a little more complicated. So what they did, instead of doing it that way, we can work on both sides of the equation. So they squared this whole problem and get the m squared equals x. And I do the derivative of both sides, which is what I was going to do anyway. That's how you got the dm. So if the derivative of that one is 2m dm, derivative of that's dx, which is what I'm trying to replace anyway. So that m is replacing the square root of x. And then this piece here is replacing my dx. The nice thing now, since we did that, is now we have two pieces and we can do my integration by parts. So I have my u du and my v dv. So which one am I going to make my u? The 2m or the e to the m? Actually, what I'm going to do is... So remember, my algebraic is always first. Exponential is going to be last. So that's going to be 2m's there. And that's e to the m. So that just becomes e to the m. And this just becomes 2 dm. So my new problem I have is 2m e to the m minus the integral of 2 e to the m dm. So I have 2m e to the m minus 2 e to the m plus c. So then the final thing we have to do is we can't leave it like that. We have to change it all back. So we start back to the x's. So it's 2 square root of x, e to the square root of x, minus 2e to the square root of x, plus c. So sometimes, this is what I was saying, when you're looking at these problems, sometimes you have to use multiple techniques to solve out the problem. This one we had to do our simple u substitution and then integration by parts to finally solve the actual problem. The nice thing is all the problems in this section have to be integration by parts. So when you're going through and doing them, you know you're using that method. The hard part of the actual test you're going to take is it's all mixed up. So you don't remember, you don't know. It's not going to say, oh, I have to do integration by parts in this one, because it's not going to say do integration by parts on this one. It's going to give you a bunch of problems and say integrate. And you have to figure out which one it is. When we do the review, we're looking at section 7.5, which gives you all the different methods and tells you how to break them down so you can actually do that part. But right now we're going through each one individually. But I will show you how to be able to look at a problem and say, okay, this problem I'm going to do substitution on, this problem I'm going to do integration by parts, this problem I need to do partial fractions, and be able to figure that part out as well. But we learn them individually and then we put them all together. So other than that, that's the last problem we're going to do tonight. So next Tuesday, we're going to do section 7.2 and 7.3 because they're both the trig topics. So we're going to do all the trigonometry integration next week. And then Thursday, we're going to do the partial fractions. The couple things I will tell you, partial fractions is not hard. However, remembering how to do factoring and remembering how to do system of equations will be very helpful to you. So if you want to brush up on some of that on Khan Academy or one of those things, looking at some systems of equations, specifically the elimination method, that's going to be very helpful for you. So, all right. Works through some of the stuff at the end of section 7.1. Those exercises, again, if you want the answer key, just send me a quick email and I'll forward it off to you. So you get all the solutions and everything else written down so you can actually do out the problem and then check the work to the way the work's supposed to be done. So you can see if you're where you're making your mistakes if you're not getting the exact right answer. Other than that, I will see you on Tuesday.
Thank you, Professor.
You're welcome. Have a good night.
Have a good
Thank
night.
you.